will generalize the concept of Euler Lagrange equation to n unknown functions. Till now, we see that our functional was the function of only one variable, but here we have a functional which depend on n number of unknown functions. So previously our functional was look like the following way, which look like j of y is equals to the integration from a to b f of x y prime of dx. So this was our functional in a previous one, and we see what is the condition for the functional to have an extremum. We see that we use the property that variation should vanish, and then we find out we got the Euler Lagrange equation, and the Euler Lagrange equation was something like of the form which look like, let me write the Euler Lagrange equation. So the Euler Lagrange equation was del of del y f, sorry, let me erase this. So this is f minus d over dx del of del y prime f is equals to 0, and which is a second order differential equation, and we see that we have a boundary condition on a function y which was y of a is equals to capital N and y of b is equals to capital B. But now our functional is of the variable n, and this look like j of y1 comma dot dot dot, and then we have a yn that is equals to integral from a to b, the limit is same, and then we have a function capital F of x comma y1 dot dot dot, and then we have a y prime of 1 and then dot 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 y prime of n and then dx. And the same question is that we have a boundary condition, we have a boundary condition too. So let's write first the boundary condition. So our boundary condition in this case will be given by, let me write first boundary condition. So boundary condition are y sub I of a is equals to ai, and y sub I of b is equals to capital B sub I. So here's our boundary condition. There are two n number of boundary condition which we have used to determine the arbitrary constants, and for information the subscript I will run from 1 to n. Okay, as before we are interested in the necessary condition for the functional to have an extremum, and to do that we will first find the variation, and for that we have to vary our function. So our function is y sub I of x. Now we will vary it to some y sub I of x plus h sub I of x, and we need to ensure that the new varies function also satisfy the boundary condition, and for that matter we have the following condition, and that is s sub I of a is equals to s sub I of b, that is identically 0. Next we will write the necessary condition, and that was delta of j, which is the varies functional which is given by the functional y1 plus h1. The functional will depend on the vary function and then our previous function, so that we know from our previous lectures, y1 comma y2 and so on, yn of, and then we will put the values of them, and then we will find out the first order term, which is delta of j, and equate it to the 0. So delta j should be equal to 0. This is a necessary condition. So let's skip the part and see what we can do with this. So we will put these values in the integral form, and when you do that, you will find out that this become the first term will become integral. We will write both of the integral, we get integral from both of the term, so we get it outside, and then we have integral from a to b f of x comma y1 plus h1, so on, and then the second term we have minus f x comma y1 comma dot dot dot, and then y prime, and so on, and then we will put the dx outside the bracket, and then we use the previous method to reduce this form in the following form, where we have integral from a to b, then we have a summation which is goes from I is equals to 1 to n f sub y I h I plus f sub y prime I h prime I dx. We use the Taylor's theorem basically for n function, and we just write the first order term, and we neglected the second order term, which is dot dot dot, because we are interested in the variation. So our variation delta j is given by the following integral, and we know that this integral must identically equals to 0, which is a necessary condition for extremum. So this our extremum should be equated to 0, and for that matter this is true only if the function y sub I satisfies the following equation, which we call the Euler Lagrange equation. So we have f sub yi minus d over, let me just rough it, dx f sub y prime of I is equals to 0. So there are n, this is basically the system of n second order differential equation, and its general solution will have 2n arbitrary constants. Let me remind you that I will goes from 1 to n, so there are n second order differential equation. So how you will determine the 2n arbitrary constant? With the help of what we see the boundary condition. There are 2n boundary conditions, and that will determine the arbitrary constants. So that is what the Euler equation, Euler Lagrange equation, and we can write the theorem here. So what we learn in this video is the following theorem, is that the unnecessary condition for the curve y sub I is equals to y sub I of x to be an extremal of the functional, that is from integral from a to b f sub of x comma y1 comma dot 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 dot, is that the function y sub I of x satisfy the Euler equation. So this is basically the theorem, which is a generalization of the functional to n equations, and in the next video we will talk about some of the remarks that I have to make, and one of them is that it may possible that the same functional, the different functional lead to the same n system second order differential equation. It means that the Euler Lagrange equation are not unique to a functional. There are two different functional, there may be two different functional which lead to the same Euler Lagrange equation.